Hello everyone, let's continue our class. So this is the section 2.1, that means in chapter 2 section 1. Today we are going to start talking about functions. So first we will talk about the function concept. What do we mean by a function? We say if the value of a variable y is determined by the value of another variable x, then y is a function of x. So for an example, we can say let a represent the age of a US citizen. So A represents the age and B represents the number of days since his birth. So then A is a function of B and B is not a function of A. That means the age is determined by the number of days since birth. So A is a function of B. But B, the number of days, is not a function of A, which is age. So in ordered pairs, we can determine our functions in this form. A function is a set of ordered pairs in which no two ordered pairs have the same first coordinate and different second coordinates. So we will talk about it further. And the variable corresponding to the first coordinate of the independent variable and the second coordinate is the dependent variable. So let's look at this relation here. You can see in this relation we have the first coordinates and the second coordinates in the first pair and the second pair, first coordinate, second coordinate. This collection of these first coordinates are called the independent variables. So these are the independent values, the first coordinates. And the second coordinates 3, 3 and 4, these are called dependent variables, so dependent values. The first coordinates are independent and y's second coordinates are dependent. So this is a function, but the second relation, it is not a function. Why? If you look at this carefully, you can see here in these first two pairs, the first coordinate is 9 and in the second pair it's also 9, but we have two different second coordinates for the same first coordinate. 9, 9, but two different y coordinate or second value. So second variable. So in this case, this is not a function. But you don't have that situation in this first relation. It's every time whenever you see the first coordinate is always different. 1, 2 and 4. But in here we have 9 twice as the first coordinate with two different y coordinates. That's the problem. So this is not a function. Now, this is a one way of identifying functions. The other way is that to use whenever you have the graph of a function, you can see if it is a function or not a function. In this case, you can see this line 3x minus 4y equals 8. This is that line. And now if you draw a vertical line across this graph, it crosses exactly as once. So that means this line represents a function. And the second example, this is the graph that we are interested in, the blue line. And now doesn't matter wherever you draw a vertical line across this graph, it crosses exactly one place on this graph. So this is also a function or a graph of a function, or this is the function. And now if we move here, look at this circle. This is the equation of the circle, x squared plus y squared equals 1. You know that this is a circle with the radius 1 centered at 0, 0. So in this circle, if you draw a line across this graph, it crosses more than one point. It crosses here at top and here at the bottom. So that means Since it crosses more than once, this equation or this graph is not representing a function. And the same thing is happening here. This is the absolute value of y equals x. So this is the graph of this equation. This is not a function because if you draw a line, vertical line like that, it crosses more than one point here and there. So this is also not a function. Likewise, this is an easy way to identify a given equation is a function or not just by looking at the graph. Or if you have the relation like this, you can see you can check all the ordered pairs and see whether you can get with the same first coordinate and with the two different second coordinates, and in this case it is not a function. Right, so next topic is to talk about the domain and the range in here. So we say the domain of a relation is the set of all first coordinates, and the range of a relation is the set of all second coordinates. So let's look at this example. Here we have a relation with ordered pairs 19 2.4, 27 3.0, 19 3.6, like that. In this relation, if you want to find the domain, there is just a collection of all these first ordered first coordinates here in 19, 27, 19 and 22. So this is the domain contains 19, 27, 19, but we don't need to write it twice, so we write it only once, 19 and 22 and 27, like that. So these are the collection of first coordinates in this relation, and the range is nothing but just second coordinates in this ordered pair. So it is 2.4, 3.0, 3.6 and 2.4. So no need to write 2.4 twice. We write it 2.4 at once and 3.0 and 3.6. So this is the range of this relation. But again, you can see that this relation does not represent a function. Why? Because here also we have the same problem with the same first coordinate 19 here, and here also 19, but you can see with this the second coordinate is different. It is 2.4 once, and here it is 3.6. So it is, this relation is not a function. Now let's say we have a function of this form, equation of this form. So let's say we want to find the domain of this equation or this function, and this is y equals absolute value of 2x minus 1. So that means we want to find where all possible values that we can plug in for this x so that this equation is defined. So think about, you are plugging negative 5 or very large negative numbers for x. So if you substitute negative numbers for x, so you get negative value in this box or in this square root. So then you have a problem with evaluating square root of a negative number, so that leads to complex numbers. So the key here is that we need to make sure that this inside of this square root is always greater than or equal 0 or positive or 0. So that's what this inequality means. We want to make sure that this is greater than or equal 0. So now if you solve this inequality, you know we have done solving inequalities, and if you solve this inequality for x, you can add 1 each side. You can get 2x greater than or equal 1 here, and then x is greater than or equal 1/2. So these are the, so this is the inequality that represents all the possible x values that you can plug into this function. So that says your x, where whatever the x that you take, you determine to plug in here, has to be greater than or equal 1/2. So in the domain, in set notation, we can write it as all the x coordinates such that x has to be greater than or equal 1/2. So then this inside term in this square root is never becomes negative for all the x greater than or equal 1/2. So this is the one situation that we have to deal with the square roots. Look at this one. In this equation, this is y equals 3 over x plus 2. So we have a rational function here. What is the problem with this function? So we want to make sure that this is defined everywhere. But since this variable is in the denominator, sometimes if you plug in some, let's say negative 2 here, if you plug in negative 2, you have negative 2 plus positive 2, the denominator becomes 0. So that means 3 divided by 0. So that is the problem here we have. So then this y is not defined. So we want to make sure that this denominator x plus 2 is never becomes 0. So we say we want x plus 2 to be not equal to 0. And now if you subtract 2 each side, you can get x is not equals negative 2. So negative 2 is the only value that this denominator becomes 0. So in the real line, in your number line, if you plot this one, you have negative 2 at the middle here. Here we have 0, it's a negative number, negative 2 here. So you are okay with, you can plug in any value less than negative 2 to the left hand side. And also you can plug in any value greater than negative 2 to the right hand side. So as an interval notation, any value less than negative 2 can be represented in interval notation like this, negative infinity to negative 2. And in the right hand side, starting negative 2, but it's excluding, it is not including negative 2, up to infinity, then you can get this interval. Here, negative infinity to negative 2, excluding negative 2, and here excluding negative 2, starting that and go up to positive infinity. Here we have two intervals which are disjoint. We say there's no intersection, so we join them using this union notation. So this is the domain of this function in interval notation. And in set notation, you can simply say all the x values such that x should not be negative 2. So now let's look at this, the last example in this domain function. Let's look at this rational function. What is the problem with this rational function? Here also this we have this variable sitting in this denominator as x squared, and we have minus 9. And you know that this x squared minus 9 can be factored of this form. This is because this is just a difference of two square terms. So this is x squared minus 3 squared. The difference of two square terms can be factored of this form. This is a special product that we discussed in class. So this is x minus 3 times x plus 2. Those are the factors of x squared minus 9. So here we have x squared minus 9. We want that not to be 0. So that's why I'm taking here, I want my x squared minus 9 not to be 0. So that means if we add 9 each side, we can get x squared not equals 9. So now if you take the square root both sides, we can solve this one for x, and in the right hand side you are getting what? Plus or minus 3 here, because its square root of 9 can be negative 3 or positive 3. So that is what exactly we have as these factors here. So your x should not be positive 3 or negative 3. So now we have two numbers. In the last case we had only one number which is negative 2, but here we have two numbers. That's the difference. So now if we plot these two numbers negative 3 and positive 3 on your number line, you have middle 0, you have negative 3 in the left hand side, positive 3 in the right hand side. So now we want to make sure that our x is not any of these numbers, negative 3 or positive 3. So that means I can take any number less than negative 3, left hand side of the negative 3 here, and I can take any number between negative 3 and positive 3, because I know that I can take positive 3 as well, and I can take any number greater than 3. So now seems to be we have three intervals. One is less than negative 3, and another one between negative 3 and positive 3, and another one, the last one from 3 to infinity. So these are the three intervals that we have. Okay, now these are also disjoint intervals. There's no intersection, so we have to join them using this union notation. So I'm joining negative infinity to negative 3 with union with negative 3 to positive 3 union with 3 to infinity. So this is the interval, or this is the domain of that function. So it is excluding these 2 points. This is the interval notation. And in the set notation you can write it as like x such that x is not equals negative 3 or negative positive 3, like that. Alright, that's how we determine the domain of a function. Now let's move to the last topic in this section. This is the function notation. So you know that we can represent a function in this relation notation. Let's give it a name as f. So now I'm taking my relation 2, 5, 3, 8 to be f. So that means if I plug in 2 to this f function, my output will be 5. So I can write it as f of 2 equals 5. I'm plugging 2 and it's giving me 5 as my output. So that's what it represents here, 2 and 5. We can do the same thing with the second order pair. Here I'm plugging 3 to my f function and then I get 8 as my output. So this is what we mean by the function notation. This is like we are giving a name to, we are naming our relations. So this is another one. We have seen this type of equations, y equals x squared. So this can be written as a function in this form. I'm naming this function as the g function. So it is like g of x equals x squared. This is easy to understand. And another one, here my function is f of x equals x squared minus 2. So in this function, let's say we want to plug in a can be any number. So I'm plugging a to this f function, so that becomes a to the power 2, because that's what this function is doing. Whatever the number that you are plugging here, it takes the second power and subtract 2. So here I'm plugging plugging a, so it is taking what? The second power and minus 2. So let's see what happens if I plug in what? A plus 1 here. So I'm plugging a plus 1 to the f function. What it does? It is taking the second power of the number that I plugged here, a plus 1. So it's a plus 1 to the power 2 and subtract 2. So but this product, this can be distributed, this product. So this is like a squared plus 2a plus 1. And we have minus 2 sitting here. So now if you simplify, you can get a squared plus 2a and minus 1. Now, with this knowledge, we're going to talk about the average rate of a function. Let's say we have 2 points or 2 ordered pairs of a function f. x1, y1, x2, y2. Now we define the average rate of a function between these 2 points is to be the y2 minus y1 divided by x2 minus x1. That is exactly the same way that we find our slope of a line. Y2 minus y1 divided by x2 minus x1. So this is the average rate of a function as x varies from x1 to x2. That's how we define. So let's see how we can apply this in a real function. Here's an example. Let's say we want to find the average rate of a function f, which is x squared, on the interval 1 and 3. So this interval represents our x1 and x2. x1 is 1, x2 is 3. So that means I want to find how much this function changes, or the average rate of change of this function when we change x from 1 to 3. So here is how do we apply the function, this formula. We want to find the what? y2. y2 is the function value at 3 because this is x2. So it's function value at x2 minus function value at x1, f3 minus f1 divided by x2 minus x1. So now if you plug in 3 to this function, that becomes 3 squared, which is 9, minus 1, that is 1 squared is minus 1 here, divided by 3 minus 1, which is 2. So 9 minus 1 becomes 8, and 8 divided by 2 is 4. So this is the average rate of this function from 1 to 2. It's easy to use. And the next thing is, how do we find the difference quotient of a function? So difference quotient is defined in this form. Let's say we have a function f, and the difference quotient is f of x plus h minus f of x divided by h. Let's look at an example. This is the function f, which is given by 3x plus 2, and the different quotient is f of x plus h minus f of x divided by h. So now I'm plugging x plus h to my function f. So we need to be careful here. It's not just x, it is x plus h. So every x in this function should be replaced by x plus h. Here I'm taking 3 times x plus h because I'm plugging x plus h. Instead of x here, it is x plus h now, plus 2, minus, here is just fx, the same function. This is 3x plus 2 divided by h. Now, if you distribute them, do the foiling here, it is 3x plus 2h, 3h plus 2 minus 3x and minus 2. Now here, you can see here we have 3x positive, and in the other side we have 3x negative, so that cancels out. And positive 2 and negative 2, that also cancels out. We get 3h divided by h. But here h and h, it is a 1 in the numerator and denominator, is h divided by h is 1, so this is just 3. So that is the average rate of this function from this is the difference quotient value of this function. You can see that since this is the line, that is exactly the slope of this line. And now the difference quotient of this function, x squared minus 2x. Here also the same formula. We need to plug in x plus h to the function f and subtract fx function f of x and divide by h. X plus h to the power 2, because that's how function works. This function is x squared minus 2x. So this is x plus h to the power 2 minus 2 times x plus h. And then the second part, minus fx function is x squared minus 2x, the same thing, divide by h. Now we can distribute this one. X plus h to the power 2 can be written as x squared plus 2h of x plus h squared. And now if we distribute this part, this becomes negative 2 of x, negative 2h, and minus x squared in the last term. And the last term 2x becomes positive 2x, because negative times negative becomes positive. So what we have here? We have x squared and we have a negative x squared, it cancels out. And we have negative 2x and we have positive 2x, so that cancels out. The rest is we have 2h of x plus h squared and negative 2h. That's it in the numerator. And divide by h. But in the numerator, you can see that h is sitting in everywhere. H can be factored out. H is in each term here. So if you factor out h, you get 2x plus h, because it was h squared, we factored 1h out, so that becomes h, and we have minus 2. And the denominator also we have h, so h divided by h is 1, so we get 2x plus h minus 2 as the difference quotient for this function. Alright, so that's all we have in this section. So I will upload another video for this section 2.2. okay, so if you have any questions, I will be online from 5 to 6 today. you can email me, and you can talk. All right. Have a nice day.